Greetings, students. This is the second set of notes in the ES1 unit, ES 1.2, the metric system and scientific notation. You can find my notes and other resources on my website, btrachy.home.blog. And once again, you're going to be writing down everything that's in orange text, starting on the very next slide, so have something to write with and something to write on. You can type it too if you want. And if you need to, you can pause the video if you need more time. So the title of these notes is The Metric System and Scientific Notation. Put that at the top of the page, a little bit bigger than your normal handwriting, and maybe underline it. The first thing I want you to write below the title is here. Weight versus mass. Weight and mass are two different things. Weight is the downward pull of an object due to gravity. Mass is how much matter an object contains. Weight is measured with a spring scale. Mass is measured with a triple beam balance. So gravity is how much the Earth is pulling on you. You try to jump away and you get pulled back down, and that's with a certain force. Weight is based on gravity. Mass is not. Mass is based on how many atoms are contained in your body. So a way I like to remember it is if you went to a different planet, your weight would change, but your mass wouldn't. If you went to the moon, you would weigh less because the gravitational pull would be less. You'd be able to jump really high. If you went to Jupiter, your weight would be more. You wouldn't be able to jump as high, and you'd feel more pressure to stay on the ground. If you went to the moon, your mass wouldn't change. You'd have the same number of atoms, no matter what. So weight is based on gravity. Mass is based on matter. SI units. In the United States, we're used to using these non-standard units like inches, feet, degrees Fahrenheit, but that goes against what the scientific community does. And scientists in the United States use SI units. SI stands for the French Système International des Unités. I suppose that's how you would say that, if you were French. And it's a lonely, non-standard world for the United States and just a couple of other countries that don't use the metric system. Even Great Britain, where our non-standard units came from, doesn't any longer use those non-standard units. The United States is stubborn, and we think it's more convenient, but it's just what we're used to. But the metric system kind of makes a lot more sense, and I'll show you why. Look at the left side graph. That is the non-standard units that we're used to using. 12 inches to a foot, 3 feet to a yard, over 1,000 yards to a mile, 16 ounces to a pound. There's no standardization between the units. On the right side, you see the metric system, and it's just one small part of the metric system, but it's an example of how standardized it is. It's always 10 of something, or 100 of something, or 1,000 of something, like 1,000 millimeters to a meter, 1,000 meters to a kilometer, and so on and so forth. And you see the graph really illustrates how neat and tidy it is. Similarly with Celsius, we got the boiling point of water at 100 degrees and the freezing point of water at 0 degrees. That makes sense. Fahrenheit, 32 degrees and 212. That's a little arbitrary. So scientists use Celsius as well. Unless they're, meteorologists in the United States use Fahrenheit for weather. So when you watch the weather, you do see Fahrenheit, and we're used to thinking about it in terms of Fahrenheit, but all over the world they talk about weather in terms of Celsius. Sometimes you hear that as centigrade. So SI units, in science we use grams for mass, liters for volume, meters for distance, degrees Celsius for temperature. And it's important that scientists use the same units so that they can communicate effectively. If only scientists in the United States were using inches and ounces, every other country's scientists would have to convert when they were reading the scientists' work. So it makes more sense for us to change what we're doing for science. So the cool thing about the metric system is you can convert from one unit to the other really easily, from like kilometers to meters to millimeters, depending on the size of your sample. It's really easy to convert it. And that's because it's all base 10. SI units are base 10. There's different prefixes that multiply or divide the units by 10. And when you're multiplying or dividing by 10, all you do is move a decimal point. So for example, if you had a measurement of 1,000 meters, you could convert that to kilometers by moving your decimal point 3 places to the left. Kilo is 1,000 of something. If you had 100 centigrams, you can convert that to grams by moving your decimal point 2 places, because there's 100 centigrams in a gram. 1,000 milliliters, similarly, is 1 liter, 1.000 liters, just to show you how the decimal place moved. Milli is 1,000th, or 0.001. And if you're trying to do this with the old British units, like 12 inches in a foot and 3 feet in a yard, the conversions would not be as simple. So there's a mnemonic device that students will often remember in order to convert metric units. And you'll see different versions of this mnemonic device, but I use this one. King Henry doesn't usually drink chocolate milk. The K stands for kilo, the H stands for hecto, the D stands for deca, the U stands for units, which are base units, 1 gram, 1 meter, 1 liter. The D stands for deci, the C stands for centi, the M stands for milli, and those are the prefixes. So kilograms, kilometers, kiloliters, milligrams, millimeters, milliliters. And you can move from one to the other. If you have a really, really, really big measurement, you use kilo. If you have a really, 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 really small measurement, you use milli. And it actually gets smaller than that. There's nanograms too, but you don't need to worry about that now. Just as kind of a side note here, some of these prefixes you don't see that often. In the real world, you really only see kilo, centi, and milli most of the time. But you need to know how to convert, and that's why I showed you the mnemonic device, and we'll do some practice problems at the end. Another math thing that you need to know is scientific notation. It allows scientists to write really big or really small numbers in shorthand. 902 million is the same number as 9.02 times 10 to the 8th. Saves you a little bit of writing, especially if the number is even bigger. Then 0.000882 is the same as writing 8.82 times 10 to the negative 4th. When you see a negative exponent, that means the number is less than 1. It's really, really small. It's a decimal. So a number is expressed in scientific notation when it is in this form: a times 10 to the nth power. A has to be a number between 1 and 10, and n has to be an integer, which basically just means it's a whole number. It can be positive or negative. So here's an example problem for scientific notation. Convert the width of the universe from standard notation, which is shown here, to scientific notation. Now this number is an estimate for the width of the universe. I think that's 210 septillion kilometers. It's a lot of zeros there. The first thing you need to do is figure out, well, where does the decimal point in this standard notation? And it's after the last zero. If no decimal point is shown, then it goes right at the end there. And where do you have to move the decimal point to in order to make this number between 1 and 10? And the answer is between the 2 and the 1. So you'd have 2.1 times 10 to the somethingth would be the same as this number up here, this giant 210 with tons of zeros. So how many times you move that decimal point, you could count it, or I could just tell you it's 23 places. When the original number is more than 1, the exponent is positive, so the answer in scientific notation is 2.1 times 10 to the 23rd. It's as simple as that. Figure out how far do you need to move the decimal point in order to make the number between 1 and 10, so we've got 2.1, and how many times did you have to move the decimal? That's your exponent, 23. Now if you moved the decimal point in the other direction, it'd be negative 23. So here is all the stuff I had you write down. You are welcome to stop the video here and make sure you got everything, catch up if you need to. On the next slide is a handwritten version. And if I were you and I were in this class and I was really, really trying to learn this stuff, I might write it by hand first and then type it up. But that might be a lot of time. So do what you need to do to get this into your notebook. A photograph of handwritten notes works. Typing it up also works. So here's a little more practice with metric conversion. In this problem, we want to convert 45.23 liters to milliliters. So this is different than scientific notation. This is metric conversion. We're going from liters, which is a base unit, to milliliters, which is a smaller unit. So it's by looking at the mnemonic, King Henry doesn't usually drink chocolate milk. The base units are the U. The milliliters are the M. To go from U to M, you have to move the decimal point 3 places to the right. So that's exactly what you do to your number. You take the decimal point where it's given and move it 3 places over to the right, and your answer is 45,230 milliliters. So then you've converted it, and 45,230 milliliters is the exact same amount of stuff as 45.23 liters. Is just another way of looking at it. Here's another example. Convert 25 millimeters to blank centimeters. So once again, we're starting with the mnemonic. They gave us millimeters, so that's the M. We're starting all the way to the right, so we're going to be moving our decimal point 1 place to the left to get to centimeters. M to C, that's 1 place to the left. So when we move it, we start with 25.0, and we move it 1 place to the left, we get 2.5 centimeters. That's the correct answer. 25 millimeters and 2.5 centimeters is the same distance. And here's another scientific notation problem. Write the following in scientific notation. Now, this is a really small number, lower than 1. So we're going to have a negative exponent here. The format for scientific notation, remember, is a times 10 to the nth, and a has to be between 1 and 10. So where can we move the decimal point so that the number is greater than 1 and less than 10? Well, the answer is after the 2. So if we're starting with 0.0000002, we move the decimal point 7 places to the right. So the exponent is -7, and a is 2.0. So the format for scientific notation is a times 10 to the nth, and the answer is 2.0 times 10 to the -7th. Is the same number as 0.0000002. The exponent is negative anytime your standard format has a very small number, or less than 1. Okay, and sometimes you're going from scientific to standard, sometimes you're going from standard to scientific. Write the following in scientific notation. That's 5,400,000. To get our A to be between 1 and 10, we have to move the decimal point where? Between the 5 and the 4. So we've got 5.4, moving that decimal point 6 places to the left. So n equals 6. 5.4 times 10 to the 6th is the same number as that 5400000. If your exponent is positive, then your standard format is a large number, greater than 10. So that's it for the notes. There will be more practice on this stuff. And I'll take you back to this slide. This is what you were supposed to write, and this is going to go in your notebook. So you can either make a slide where you've typed everything, or you can photograph your handwriting and copy the photograph into your notebook.